Great, thanks for the introduction, normal volume. Okay, I'm Kay Ousterhout, and the work that I'll be talking about today is joint work with a bunch of other folks at UC Berkeley, especially my advisor, Sylvia Ratnasamy. So I want to start by just giving a little bit of background about me, very briefly. I currently work at a startup called Kelda, and I won't be talking about what Kelda does at all today, except very briefly right now, to tell you that we make it much easier to launch software like Spark in the cloud. So if you're curious and check it out and try and launch a Spark cluster, there's a URL up here on the screen. And then similar to Colleen, all of these slides will be posted afterwards, so you don't need to take photos or anything. So more relevant to this talk, I'm on the Spark PMC, and as you said in the intro, all of my PhD thesis work has been on understanding performance of Spark. There were sort of two chunks to that. The first was doing a bunch of measurement work to understand why Spark is slow and how we could speed it up. And then the second chunk was basically ripping out all of the internals of Spark and rewriting them to try and make it easier to reason about performance. And that's what I'll be talking about today. Great. So I just want to do a quick poll here to get a sense of folks' backgrounds. You asked how many people have run Spark. I'm curious how many people have modified the internals of Spark at some point or work on them. A few people in the audience. Okay, cool. So it sounds like most people look more like this person, where you're running a workload on a cluster of Spark machines, and usually pretty quickly you ask this question of, what can I do to make my workload faster? And luckily for you, Spark today includes a ton of different ways for you to do this. There are a bunch of knobs that you can turn to adjust the performance of your workload. And just to give you a sense of some of the things that I'm sure you've probably already thought about when you're running Spark workloads. One thing you might think about is, should I use a different cloud instance type? You know, EC2 has dozens of different types of machines. There was some work at Berkeley recently that showed that even if you fix the budget, you can typically make things as much as twice as fast if you just pick a slightly different machine type, like with a different ratio of CPUs to disks to network. Another thing you might ask about is changing the software configuration. Like maybe I should use a different compression or serialization library to make a somewhat different trade-off of CPU for I/O. So there are a ton of different options as you answer this question, and you probably know that if you get these things right, you can improve the performance of your workload a ton. But fundamentally, the problem is that there's not a good way to answer these questions. You're kind of flailing in the dark. And to make matters worse, you know, Spark once had a few knobs, and increasingly, this animation is slow, but increasingly there are more and more different things that you can change about Spark, which both means that there's more choices for what you can change, and it also means that it's harder to understand what's going on. Can make this work. Okay, so the basic idea behind all of this work that we did is that there's massive performance improvements that are possible just by things that users can change. And this is great news if you're a user. It means that you don't have to wait for somebody who works on Spark Core to go change something to make your workload faster. But fundamentally, the problem is that you don't know which knobs you need to turn to do this. So for those of you sitting in the audience who work on Spark Core, in this talk, I hope to convince you that this is really important, that basically we should be doing more to try and help users understand how they can make their workloads faster, and that helping users just tune all of the existing knobs that already exist is much more useful than adding that one extra optimization that now someone has to decide whether or not they want to turn on. For the folks that are using Spark in the audience, I hope this talk will give you a sense of what's actually going on under the covers, so you can do better tuning of your workloads currently. So I'll start by talking about some work that we did in the past to measure performance of Spark, and I'll talk about where we added instrumentation and how you should interpret the results of that. Next, I'll talk about some research work that we did that's much more future-looking. This is what I mentioned before, where we essentially ripped out the guts of Spark and rewrote it to make it much easier to understand what's going on. And then finally, I'll take a more practical angle at that future-looking work to talk about how some of the lessons from that can be applied back to Spark today to get a better sense of what's going on with your workloads. So first, let me start by talking about instrumentation that exists in Spark today. And to do that, I'll start with this example Spark word count job, which probably everyone in the audience has seen a job written somewhat like this. This is written in Spark's Python API. So this job has two parts. The first part of the job is reading in a file from HDFS and splitting it into a bunch of words, then emitting a count of 1 for each of those words. And then the second part is combining all of the counts and saving the output. And many of you probably know that what this looks like is it will be split into a map stage and a reduce stage. And at a very high level, what a stage is it's just a group of tasks that all do the same thing, but on a slightly different piece of input. So for example, for the map stage, all of the tasks read a little bit of input data and emit those counts, and they only differ in the data that they do so for. So zooming in a little bit further, let's look at exactly what one of these reduce tasks is doing. So here I'll show what's happening over time. There's a main compute thread in the task that's doing some things, and then the task is also using the network and the disk in the background. So this is a reduced task. So at a high level, what the task is doing is it's reading a bunch of data over the network, and then it's trying to combine all of the counts for a bunch of different words. So the first thing that the task will do in Spark is it will request a bunch of shuffle blocks. This is data that's on a bunch of remote machines. So each one of these blocks is the time to handle one of those shuffle blocks. Then at the same time, the task will read some data locally from the local disk on the machine because the data is spread across the cluster, so some is remote and some is local. When those reads finish, the task will start processing that local data, so it'll keep doing this as it gets more local data. And then as it generates output data, it'll write that output back to disk. So what you should be starting to get a sense of here is that the Spark task is doing a bunch of different things at the same time. And this process will continue. The task keeps using this fine-grained pipelining to parallelize the use of a bunch of different resources. And the reason that Spark does this is for efficiency. If you use a bunch of resources in parallel, at the same time, all of the tasks complete more quickly. So this is the kind of, if you get one takeaway from this talk, it should be that each task in Spark is doing a bunch of different things, and it's changing at very fine time granularity. So if you've ever wondered, like, why can't Spark just tell me something really obvious about what's going on in my job, this is kind of the fundamental reason. If you ask even a really basic question, like, what's the bottleneck for this task, this seems like a question that should be easy to answer. But when you look at this picture, you can get a sense of why that's not the case. Like at the beginning, the task is bottlenecked on the network and the disk. Then there are points in the middle where the task is bottlenecked on other things. Like here in the middle, the task is bottlenecked on the network. And then at the end, the task is bottlenecked on the CPU. So there's not a simple question to even this, a simple answer to even this basic question of what is the bottleneck. So going back to sort of reality, like what instrumentation exists today? What can you do if, what does Spark show you when it's running, when it gives you metrics about the tasks that are running? So essentially all of the instrumentation that exists in Spark is focused around this main compute thread for the task and measuring what that's doing. So for a shuffle task, for example, Spark will tell you all of the time that it's blocked waiting to read shuffle data. And you'll notice that this is time both using the network and using the disk. It may be either one of these things, and this is not separated out. Now, the other thing that Spark will tell you is the executor computing time. And you can already notice sort of a problem with the existing Spark instrumentation. We call this the computing time, but this is kind of a lie. It's basically just the leftovers of everything else that Spark couldn't account for. So in this particular example, there's this disk right at the end here. That's this orange block. And ideally, Spark would tell you that that's the time to write output data, but instead, Spark tells you that that's the computing time. So this is another kind of gotcha to know as you're looking at the metrics that Spark tells you is that this executor computing time is basically the leftovers. It's the things that we couldn't account for you, but it's not necessarily just time using the CPU. But this shuffle read block time can be important for diagnosing when it's taking a long time to read the shuffle data. So this is what things look like now. Now, how many of you have looked at this event pipe timeline view when you've been running a Spark job? Okay, so some chunk of people. And one thing you might notice is that the picture here of what's happening for each task looks somewhat different than the picture I drew where the task is alternating what it's doing at this kind of fine time granularity. So what the UI is showing is it's combining all of these times. Spark just adds up all of these times and shows them to you like this as if only one thing is happening at a time, but that's not actually what's happening under the hood. So this is another thing that can be somewhat misleading and I think is helpful to know as you're diving into trying to understand what's actually going on. Cool. So the instrumentation today, just to summarize, is all centered on this single main task thread. The most useful things that Spark reports about this right now are the time to read and write shuffle data. Somewhat recently, Spark also added instrumentation for the task CPU time. So in theory, that would tell you only this purple when the task was actually using the CPU. But unfortunately, this depends on which JVM that you're using. So it'll show 0 if it's not accurate. So you'll know. Now the bad part of this is that the input read and the output write times are not instrumented. And this is often a cause when we did a bunch of measurement to understand what makes Spark workloads slow. This is one of the most common causes of slow tasks or of straggler tasks is that it's taking a long time to read or write data, especially if the data is stored on disk. So I want to take a few minutes to talk about why this is difficult to add, but also a great project for somebody who's interested in adding some more instrumentation to Spark. So before I drew this picture showing what's happening when the shuffle data is computing and writing data to disk, and this was sort of this nice picture where Spark is processing one shuffle block at a time. And there's one fundamental problem with this diagram, which is that it's a bit of a lie. And instead what it looks like is Spark uses this old technique from the 80s called the volcano operator model, where it actually processes one record at a time. So the compute thread will compute on one record and then write it to disk, and then compute on the next record and write it to disk. Most of those writes will get buffered, so they happen really fast, and then occasionally the buffer will fill up and they'll get written to the disk. So the problem with this reality is that it means that you can't instrument things easily in Spark. This has been added a couple of times in Spark and then subsequently quickly ripped out when people realize that it makes everything much slower, because you just can't add timing for every single record. And the problem here is that Spark doesn't know when the buffers get flushed. Like, what we really want to log is only this time when that big buffer is getting flushed to disk. And the problem is that that's usually happening in some lower level system, like in the operating system or in HDFS, where Spark doesn't have access to it. The good thing is that HDFS does know this, and so this instrumentation can be added in HDFS. We did this in the context of the research project that we worked on. It's not very difficult to do. It just involves adding a lot of plumbing to HDFS and then to eventually pass this into the statistics object that goes back to Spark. But this is the first thing I'll sort of mention as a great project for somebody who's interested in adding something very helpful to Spark. This is something that a lot of folks could use or benefit from. Okay, so just to recap the kind of state of the universe today, tasks use this fine-grained pipelining to do a bunch of different things at the same time. Spark has some instrumentation for this. It's all based on that main compute thread. So it's only measuring the time when the tasks are blocked waiting on something. And there are a bunch of opportunities to improve this. Like, with not huge engineering effort, we could make these metrics much more useful to people to try and to help them understand if their I/O time is the thing that's actually dominating. So we talked a little bit about the past, about the stuff that already exists. I'll spend the next couple of minutes talking about the future, a different way we could have architected Spark that would make it much easier to reason about performance. So to return to this high-level picture of what happens in a task, the kind of root cause of the reason that this was very difficult to reason about is that each task was using fine-grained pipelining to use a bunch of different resources at the same time. And just to belabor for a minute why this made things really painful to reason about, if you zoom back out, there are a bunch of tasks running in parallel on each machine, and all of these tasks are doing different things at different times, and they're potentially contending with each other. Like, these are a bunch of reduced tasks, and when they start, they'll all contend for the network as they're requesting data. So this makes it harder to reason about, because my task could be blocked on the network because I requested a lot of data, or it could be blocked on the network because someone else requested a lot of data and just happens to be running on the same machine, and my network reads are stuck in the queue behind them. So returning to this kind of basic what's the bottleneck question that many people want to know, I talked about earlier why it's hard to answer for a single task, but this gets even more ugly when you have a bunch of things running in parallel, and at any given time, all of the tasks on the machine may be bottlenecked on different resources. Now, if you kind of zoom back out to the user that we talked about in the beginning and the kind of question that she might ask, like, how much faster would my job be if I used a different EC2 instance that had twice as much disk throughput, you can see pretty quickly why essentially no amount of instrumentation is going to allow us to answer this question in Spark today. Like, if we wanted to answer this question, we would have to walk through all of these tasks at the granularity of the pipelining and first say, how would the timing for these disk writes change? And then how would that change the timing of how the tasks use other resources on the machine? And you can see pretty quickly that this becomes way too complicated to be feasible. So this is the kind of key challenge today, is that tasks use many different resources. The idea of this research project was very simple. It was, let's instead architect these systems where a job is broken into monotasks, and each monotask only uses one resource. So if this is what things look like today, this is a task that's parallelizing the network, the CPU, and the disk. With monotasks, this would instead look like 3 different tasks, one that uses each resource. So first, one that uses the network, then one that uses CPU, and finally one that uses the disk. And one important thing about this is that there's these hard dependencies between the monotasks. So for example, the compute monotask won't start until all of its data has been read over the network. And this ensures that each task uses the underlying resource completely. The other important part of this design is that there's a dedicated scheduler that controls each individual resource. So the network monotask is scheduled by a network scheduler. The CPU monotask is scheduled by a CPU scheduler. And you can start to see how this design makes it possible for schedulers. Each resource scheduler has total visibility about the underlying resource. So they can very simply ensure high utilization on the machine. Like the CPU scheduler kind of trivially can run one thing on each core and make sure that the CPU stays fully utilized. And then similarly with the disk, you can run one monotask on each disk. So this process continues as you schedule more tasks in the job. So just to recap, there's two important things about this design. The first is that each task is only doing one thing. And the second is that you're scheduling each resource with this dedicated per resource scheduler. I won't talk much more about this, but the high level results from the research project on this were that we can get performance parity with Spark even using this completely different design where we broke out the use of different resources. And at a high level, sort of intuitively, the reason why that's possible, and in many cases we can get better performance in Spark, is because of these per resource schedulers that can make sure that each resource is fully used. The more important takeaway, I think, in the context of this talk is that by breaking tasks into these different units that only use a single resource, you get this out-of-the-box, very simple performance telemetry. Like, you know exactly how long all of the compute monotasks for your job took, and the disk monotasks and the network monotasks, so it's very easy to report to a user, here are exactly the resources that contributed to the runtime of your job. I just want to talk very briefly about one example why that's useful, and that's that you can answer these sort of what-if questions for users who are thinking about reconfiguring their job in a different way. So to consider one example, if a user asks, how much faster would my job run if it had 4 times as many machines? So with additional machines, in this particular case, there's enough space to store all of the input data in memory, which means that there's no time to do the disk read, and also there's no CPU time needed to deserialize the data from disk. And then the final change is that all of the machines have flash drives instead of disks, so this means that the shuffle data will be faster to read and write. So this is kind of a massive change, but it's the kind of thing that a user might consider as they're thinking about how to improve the performance of their workload. And what this graph shows at a high level is that once you use monotasks, it becomes trivial to make these kind of predictions because you know exactly how long the job spent on each resource, and so you can estimate exactly what the change would be if the underlying resources were different. So what this graph is showing is 3 different workloads. The leftmost bar is the time on the original cluster. The middle bar is the time on the new cluster that we predicted using these monotask runtimes and some very simple arithmetic. And then the rightmost bar is the actual time when we ran it on the new cluster. And the takeaway here is that we can correctly predict that these workloads all improved by about a factor of 10 as a result of all of these changes, and we can predict it with very low error. So the high-level takeaway from this project is that if we break jobs into single resource tasks, we get this performance telemetry that's very useful for providing metrics to users to understand their workloads, and we can do so without sacrificing performance. Now there's a kind of major gotcha with this project, which is that the project is API compatible with Spark, but it's a massive change to Spark's internals. The current implementation is sort of tens of thousands of lines of changes to Spark, and it doesn't support everything that Spark supports, like it only supports one cluster scheduler. So this is something that's really not feasible to merge into Spark anytime in the near term. So I'll spend the last couple of minutes here talking about the present, how we can take those lessons from monotasks and apply them back to Spark today to make it easier to reason about. So looking back at monotasks, the key idea here was that if we have these single resource tasks, we can give users kind of perfect performance metrics about what's going on in their job. So the question that I'll ask in the last few minutes here is like, is there anything we can do, given that Spark looks like this now, to give users a picture that looks more like this, where we tell users like, oh, your job used exactly 10 seconds of the network and 3 seconds of CPU time and 15 seconds of disk or something like that. Is there any instrumentation that we can add today to get monotask-like metrics? And I think if you had asked me this question a few years ago, I would have told you that this definitely wasn't possible. And let me just walk through for a minute why. Intuitively, this seems difficult to do. So if you ask for a particular task, like how much time did it spend using the network? one tempting thing you might say is like, can we just measure the resource utilization on the machine and see how much network was in use? But zooming back out, in Spark, there are a bunch of tasks that run in parallel, and they're all running in the same JVM. So if we just get the machine level resource utilization information, we can't untangle all of these different tasks that are running. And we can't understand how all of these tasks are contending, because all of that contention, in the case of the network, is being handled in the OS networking stack. So there's not any easy way for Spark to get metrics about if my task is waiting on the network, like what exactly is happening and how much network was getting used in the background while I was using the CPU. So the challenge here, and I think why it's easy to say that this might not be possible, is that it's hard to untangle all of the tasks that are running on a particular machine. But it turns out with some tricks, we can get near perfect information about this, because Spark does have information about the total amount of data that was read over the network, like, oh, my task read a gigabyte of data. And then the real challenge here is answering how long did it take to read that data. And it turns out that that question you can answer using the machine utilization, or you can make a very good estimate of it with the machine utilization. Like, you know that on average, the machine had some network bandwidth across all of the tasks. So you can use that to make an estimate of, given the amount of data that the task read, how much of the network time on the machine was the responsibility of this one particular task. And you can do exactly the same kind of thing with the disk I/O to get these estimates. So to recap, if you take the existing per task total data counters about how much data was read or how much data was written and combine them with the machine level utilization metrics, you can get these sort of near complete metrics about exactly what was going on while a particular task was running. So you can get something very similar to what we could get with monotasks to allow users to do these sort of what if things, like what if I had twice as many disks, how much longer would my job have taken to complete? Or hopefully how much faster would my job have completed? So the goal of this work overall was to provide performance clarity. And before I wrap up, I just want to reiterate for a minute why this whole thing is something that we care about. I think for the folks that are working on Spark, the way, or any sort of arbitrary system, typically the way that you evaluate performance is you have a small group of experts that spend a lot of time tuning the system to perform at its best. But in reality, what performance typically looks like is there's one person or maybe a small group of novices who are running the system, and they don't know how to do the same tuning that the expert is doing. And I think one example where you see this a lot is where a particular company publishes some benchmark results. Like Databricks will publish some benchmark that says Spark is much better than Flink, and then everyone who works on Flink says like, oh, no, you didn't configure it correctly, and then the opposite thing will happen. And the reality is like, this is our fault that people can't configure the system properly. Like, this is something that we need to be thinking about more. Some person who's a systems expert who knows how to run some other system, that person, if anyone, should be able to figure out how to configure Spark correctly. And if they can't, we should be thinking about how to build the system in a way that makes this easier for them. Cool, so the other things that I mentioned in this talk is the instrumentation that exists already. It's mostly focused on the block time from the perspective of that main task thread. But with some improvements, we can get information about sort of everything that the task is doing, even in the background, and even when it's competing with other tasks. So there's 3 specific things here that I think could be added to Spark, and none of these are a huge amount of work. I think these are all things that could be done in a couple of days. So if anyone is interested in this, I think there would be I certainly get a lot of emails from people who ask for these things. So I think a lot of people would be interested in using this. So with this, I'm happy to take any questions. Yeah, so the question was with monotasks, how did we decide how long each of those monotasks should be? We made a super simple decision for this, which is that we just took the existing Spark tasks and split them into a network part and a CPU part and a disk part. So we would do the entire network read that a particular task would do. The kind of intuition for why this works well is that there are typically, for most workloads, already enough Spark tasks that you get a pretty short read. So you don't end up with huge head-of-line blocking issues. But yeah, this is one kind of tricky tuning issue you would need to get right.
Did you check, you had instrumentation to find whether or not you had line blocking?
Yeah, so the question was, did we add instrumentation to find whether you have head of line blocking? One thing that's cool about this design is you get this kind of out of the box instrumentation for things like this. Like every job has instrumentation about how long did its monotasks spend waiting in a queue. So yeah, we have instrumentation for exactly this. Like a job can report, I got stuck for 20 seconds behind something slow. Any other questions?
I remember reading about a profiler where to kind of figure out if a faster CPU would be interesting, just slow down everything else, right? How do you think about these approaches?
Yeah, so the question was, you read about a profiler where to figure out how much faster something can be, you slow down everything else. I think maybe you're thinking of, there's this project called Cause that did this. And there's also some work at Berkeley that's trying to do exactly this thing. And I think there's a lot of projects that kind of fall into this broad category. Like, can we take this system that's really complicated and treat it as a black box and still be able to understand something about performance? Which I think is very important given the sort of practicalities of like, we're somewhat stuck with these systems today. But the goal of some of this work, like the monotask stuff, was to think like, if we were to start from scratch again, could we make all of these things really easy so you don't have to do complicated things like that? And it's pretty difficult to do that. Like, it is doable, but actually slowing down every single use of a particular resource to estimate something is sort of painful and not something that you can do online. Like, then you have to go run your workload in some different use. Yeah. Cool. Sure. Yeah.
So with all the knobs, have you seen anybody treating the optimization problem as a machine learning thing?
Yeah, the question was, with all the knobs, have you seen anyone treating the optimization problem as a machine learning problem? And yes, there are also folks at Berkeley who have done exactly of this thing. And the problem with that, again, is that you have to do this offline training. And all jobs are different enough that there's no model that works for everything. So how those things typically work is they'll take a part of one job and they'll run it like 30 times on a bunch of different configurations and then train a model just for that one job. And again, this is the kind of thing that's like, it works, but it's not something that's really practical. Like, as a user, I can't take every single one of my workloads and run it 30 times to decide what the best performance is. And I think kind of fundamentally the reason why you can't build a more general model is because what's going on under the hood is so complicated. Yeah. Cool. Thanks.